Okay. Welcome to Tools of Operations Research. This is lecture number 6. We're going to begin by revisiting what we talked about last time in lecture 5, specifically in assignment number 5. We're going to actually go over one of the problems from that assignment. We'll go over the fourth exercise, or the fourth question. So I have that up here. It involves, a company, there are fixed costs associated with paying your sales force that you have to pay if you're going to sell that particular product. There are 3 products. They're just called I, J, and K. There's a maximum demand on those products. That is a maximum amount that we believe can be sold. And there is a per unit profit amount that's known per product. So for product I, we believe we can sell 290,000 units for a $1.20 profit on each one. Okay. Now, to make these 3 products, each one requires time spent on 3 different machines. So we've talked about examples like that before. In this case, we didn't give those machines names. We just called them A, B, and C. And we have listed here the number of hours needed on a particular machine to make 1,000 units of each product, and each machine has a total number of hours available. Okay, so right away you can kind of see the constraints are going to be, well, obviously the objective is to maximize profit. Okay, so profit is just going to be how many units we sell, that is how many we can make, less than the demand, how many units we sell times how much profit we can make by each one, minus costs, okay, which in this case there's only a fixed cost. The variable cost you can assume is kind of rolled into the per unit profit. That is, if it cost 80 cents to make and we sell it for $2, then the overall profit is $1.20. Okay, so we kind of assume that variable costs are already built in to the variable profit. And so there's only fixed costs involved. But we only want to pay those fixed costs if we're going to make any of that product. That is, it may turn out the optimal solution, because of our constraint on number of hours available at each machine, it may turn out that it's only optimal to build one product and pay one sales force team to sell that product and make the maximum profit. Or it might be optimal to build or make 2 of the products. It could be optimal to build all 3. So that's what we need to find out. So here we have all the numbers. I'm going to try to transcribe these into Excel. Okay. So we have our products, I, J, and K. And I'm just going to list out the various parameters that are going to be used in our model. So we know the demand for each product. We know the profit contribution for each product. That's per unit. And we know the fixed costs associated with paying the sales team to go out and sell the product to our customers. Okay. And then we also know machine hours needed for each product. That is for 1,000 units of the product, so we'll need to make sure we account for somewhere either dividing by or multiplying by 1,000. Okay. For each machine, we know some available number of hours. Okay, so that should capture just the parameters of the situation, the model that we believe is accurate for the world. That is, how many product units we can sell, how much we're going to have to pay our salespeople to sell them, how much profit we make on each one, and how long it takes on each machine to build each product. Okay. So the decisions we need to make, or the variables that we need to make, are how many of each product should we sell. Okay? So I'm just going to call this how many, and we're also going to decide if we make any of a product. Okay? So we're actually going to have 6 decisions to make. Okay? And the way we're going to set up our constraints in a minute will make it clear why we actually choose to have 6 distinct decisions, even though 3 of them are going to be correlated or related to the other 3. So for example, we're going to constrain that the if we make product I, J, or K, this to be a binary variable. It's either 1 for when we want to make that product, or 0 when we don't want to make any of that product. And then the how many is how many units. Okay? That can be 0 if we're not going to make the product at all. If we're going to make more than 0 units, so up here, if we want a value greater than 0 in this top row, the corresponding value underneath it has to be 1. Okay? And we're going to enforce that via a constraint. What that's going to allow us to do is the binary variables here, whether or not we make a product, it'll be easy to multiply that by the fixed costs. Because if we're not going to make the product, then 0 times the fixed costs is 0, meaning we don't have to pay the fixed cost because we're not making it. Whereas if the binary decision variable is 1, we are going to make that product. 1 times the fixed cost is just the fixed cost. So it allows us to easily compute how much contribution those fixed costs are going to have in our overall profit. So we can compute, well, I'll break this down. So let's compute our revenue, our costs, and then the final objective, which is profit. Okay. So the revenue is how many units we're going to make of each particular product times the per unit product, or per unit profit. Okay, simple enough. So we'll copy that equation over so you can see that. So each time I'm just multiplying the decision variable of how many to make by the per unit profit. That's the revenue. That's the money coming in. The costs, we only have fixed costs we're worried about here. So the fixed costs are just whether or not we make the product times the fixed costs we know we'd have to pay if we do make it. Okay. And then the final profit, well, we can sum these easy enough. So sum of the revenues, sum of the costs, and the profit is just going to be revenue minus cost. Okay. So the sum of how much profit we make selling each of the products, however many we sell, minus the costs we're going to pay, the fixed costs we pay for each of the products that we do decide to make. Okay. All right. So now let's start talking about some of the constraints. Okay. Just any one of the revenues. So I'm doing C10, that is the how many units to make decision variable, multiplied by the per product or per unit profit. Okay. And then those 3 values I'm just summing up. Okay. And total profit is going to be our objective. Okay. So I'm just going to format, make this look a little nicer so we can see what's going on. All right. So one of the constraints we have is that we can't use more than the available number of hours for machine A. Okay. So what we need to know is how many hours of machine A's time do we need. So that's going to be, and I'm going to calculate that per product. So how many I's we make divided by 1,000, okay, multiplied by the number of hours each 1,000 units of I take on machine A is how much time of machine A's time we would need for the number of product I units we're going to make. Okay. So in my case, C10, the decision variable for how many to make, I'm going to divide that by 1,000 because I need to know how many thousands of those I'm going to make. and multiply that by the number up here, which is the number of hours it takes to make 1,000 of those products. Okay, and I can do the same for all of the products, I, J, and K. And I can do something very similar for machine B and machine C. Okay, I'm actually going to change the C10 here to be an absolute reference to row 10, so that I can actually copy this both over and down. And that way you'll see it's always, for the product I, it's always multiplying C10, how many product I's we're going to make, by the corresponding machine number of hours it takes to make 1,000 units. Okay, so each row I'm just going to sum up. So that's, first row is how many hours of machine A's time we will use, and we're going to constrain that to be less than or equal to the available number of hours for machine A. Okay, and so forth. Just copying all those formulas down. So how many hours of each machine's time we need to make the number of products we want to make, and we're going to constrain that somewhere to be less than or equal to the number of hours available for the machines. Okay. Now, the other constraint, two other constraints we need to add. One is we need to make sure we don't make more of a product than the demand for that product. Okay. So if we could only sell 290,000 I units, we don't want to make more. We want to constrain the solution to not make more than that. Okay. We also need to constrain those pairs of decision variables that say, if we want to make more than 0 units of I, then the second decision variable, the binary decision variable, needs to be a 1, not a 0, which means we will end up paying the cost, the fixed cost associated with that product. I'm going to combine those two constraints, okay, into a single constraint for each product. I'm going to show you how that's done. Okay, so let's say this is the demand for product I. Okay, and what I'm going to do is I'm going to say, actually we'll just use some product to multiply how many of each thing we make by this line here. So we're only interested in product I. I only have a 1 there. And I'm going to constrain that to be less than or equal to, okay, the demand. Except instead of just saying the demand for I, okay, I'm going to multiply that by whether or not we choose to make I products. Okay. So let you see that. Okay. So what I'm saying is the number of units of I you make has to be less than or equal to the demand for I multiplied by whether you chose to make it. If you didn't choose to make any, if the decision variable for making I's is 0, then 0 times this demand parameter up here is 0, which means this constraint effectively says you can make no more than 0 product I's. Right? You have to choose to make 0 product I's because the demand for it would technically be 0. Okay? If I chose to make I's, so I put a 1 in the decision variable, then 1 times 290,000, the demand for I's, just means that this constraint says you can make up to 290,000 units of I. Okay? So this constraint, between that equation there where I multiply the binary variable by the real demand, and all I'm doing here is I'm computing how many, basically I'm just saying how many I's did we choose to make, the how many decision variable. And I'm saying that value has to be less than the demand times the binary variable of whether or not we choose to make them. Okay? And that effectively links these two decision variables. That is, the binary decision variable controls the constraint of how big the value for the non-binary decision variable can be. Okay.
What's the C21 there?
C21, just 1. Yeah, and that's just so I can use some product over here because I'm just going to copy that down and do the same for all I, j, and k. There's no particular reason why you would have to do it this way. It just makes it for easier copying of the formulas, and it makes it all symmetric. So it's easier to understand. So the demand for j is the binary decision variable of whether or not we're going to make j's multiplied by its real demand. Okay? And the constraint for how many k's we make is going to be the binary decision variable for if we make them multiplied by its demand. Okay? Okay. So we have, in this case, 6 constraints, although 3 of them are kind of like a dual constraint. Okay? We're going to add a few more constraints, which is we're going to make sure that you can't choose to make negative of anything. That wouldn't make sense. And we also need to constrain the binary variables to be binary. That is, the solution can only have 0 or 1 for each of those. So let's go ahead and define the model. So I'm going to highlight all 6 decision variables. Click the Decisions Normal button, like we would normally. I'm going to highlight my profit, my objective here, and say that's the objective that I'm wanting to maximize. I have 6 constraints here, sort of at the bottom of the sheet, that I all want to constrain to be less than or equal to the corresponding cell in column H. And then I'm going to constrain the last 3, or the bottom 3 decision variables. So I'm just going to say constrain to be equal, but instead of saying equal, I'm going to use this drop down to say these need to be binary. So BIN, which stands for binary. So I was just saying the only values you can choose to put in C11 through E11 are binary values, 0 and 1 only. Okay. And then instead of creating a constraint that says all of the first 3 have to be greater than or equal to 0, I'll just use the nice option we have on the Engine tab to say assume non-negative is true. That is, assume you have to choose non-negative values for things, 0 or positive. Okay. And this should be a linear problem, so let's select the linear engine. You wouldn't have to do that. You can let it automatically select, but this will help us ensure that we've created a linear model and it's solvable by the linear solver. So let's solve and see. Okay. So in this case, it says it found a solution. All constraints and optimality are obeyed or are adhered to. And what it actually found was it's only suitable, okay, to make product J, although it looks like we're making too many, so something's gone awry. Oh, when I copied that formula, I didn't properly ensure that my row values were, let's see here. My row values were correct. Yep, so there. What it found was I allowed it, I broke my linking constraints and my demand constraints, so it both produced more than the demand and didn't choose to pay the fixed costs. Let's solve that again now that I fixed my formulas. There we go. So in this case, the optimal solution says, let's make these dollar amounts. The optimal solution says we can make $348,000 by making all of the I products that we can and all of the K products that we can. Okay? And what we've technically done, well, let me ask, so what are the binding constraints in this problem as it's listed here? The demand, yeah. So we only produced as many I's and J's as demand would allow. Those are binding, definitely. We could ask the question of why didn't we produce product J? Okay. And the answer should be somewhat intuitive. Product J makes a modest profit per unit. However, it comes with a very high fixed cost. Okay. Which means if we're trying to maximize profit, it's only worth making product J if you can make lots of it. Because you'd have to make a lot of revenue from a lot of J product or a lot of J units to overcome its fixed costs. Okay? And we chose not to do that, probably, most likely, because we didn't have enough machine hours to make enough J product to overcome its fixed cost and actually turn a profit for product J. That is, we would have actually reduced profit by making all the J's we had time for on whatever machine is the one that probably takes the most time for J's. Okay? So we chose not to make any J's at all. Okay? This is the exact kind of problem where these linking constraints come in very handy. When you have these fixed costs that you're unsure, is it better to pay the fixed cost so that I can make a more general decision, like how many things to make, or do I save money by not making any of them and not paying the fixed cost at all? In this case, the answer was, at least for product J, it's better not to make any product J at all. Okay. All right, so that was assignment 5, exercise 4, at least part A or so. So that was determining which product should we produce. In this case, it was I and K, and how many. In this case, the best was to produce as many as we could, as many as demand would allow. So let's go ahead and talk about part B. Suppose the demand potential for product K were doubled. What would be the maximum profit contribution? Okay, so just so I can keep track, this was K demand. When it was 50,000, then our profit was, let's paste the value here, 348,000. Okay, so we're going to double this demand for K. So instead of 50,000, we'll do 100,000. So now the demand for K is no longer a binding constraint, so let's resolve and see if we would make more K product. And of course, as you might expect, we would. However, we don't make as much as we could sell. We're probably constrained by one machine, in which case it looks like machine A, so we're using all of machine A's time making the 290,000 I products and the 61,000 and some K products. Okay. But we did get a better profit. So if demand for K were doubled to 100,000, then we could turn a better product or a profit. Okay, let's see what the difference is. So a $25,000 better profit for K. For making more Ks, given that we have a higher demand for the K product. Okay, so that would be my answer to part B. Okay, you might have to spell that out a little better than what I did here, but this kind of summarizes K demand of 50,000, you get this much profit. K demand of twice that, you get this amount of profit, and this is the difference. Okay. All right, let's do part C. Still with product K demand doubled, which machine's hours available is constraining the optimal solution? So we talked about that. It's machine A whose hours are constraining. Suppose you reduced the number of hours available of another machine by 100 hours and increased the constraining machine's hours by 100. That is, imagine we could take people who work on some other machine and assign them to working on machine A and technically have more available capacity for machine A, that more hours of work it could do more people working with it. Okay. What would the maximum profit contributions be? Which other machine did you choose, and why? So let's just see. We could take 100 units away from machine B and add 100 to the available hours of machine A, or we could take 100 hours away from machine C. I don't necessarily know which one might be better. Okay, so let's just try. Let's just try machine B. So if I took 100 units away from B and added 100 units more to A, okay, so we'll say this is machine B hours reduced. Then let's solve. And here's the profit we would get. Okay. So a better profit than what we got before, because obviously machine A had more hours. Previously it was constraining the optimal solution. Now it's not. Now machine B is constraining. So the machine we took hours away from has now become the machine that constrains how many I's and K's can be made, and hence how much profit can be made. Okay? So let's imagine, what if we reduced machine C's hours? So I'll put 100 back into machine B's hours available and take 100 away from C. Rerun. Okay. And it looks like we can get a better profit by taking hours away from C than we can taking hours away from machine B. And of course now machine C has become the binding constraint instead of A or B. Okay. So that's one way you could have answered part C to the question, right? It's just asking, if you took 100 hours away from B or C and added that 100 to A, what better profit could be achieved? And in this case, I didn't choose one or the other. I actually did both, just the C. Okay. Now that I know the answer, obviously I would want to choose C, because taking hours away from C allows us to get a higher profit than taking those same number of hours from machine B. Okay. That's assignment 5. Are there any other questions about assignment 5? Okay.
Small doubts and making them at the end of
I'm sorry?
I have very few doubts and small doubts
Okay, just small things.
at the end.
Okay, yeah, maybe we can look at those individually later. Okay. As far as the other questions, I'll bring it back up here. As far as the other questions on the assignment, did they make sense? So, first question, sort of just a typical linear optimization problem where we have cars we're going to make. You can make so much profit for each one. You can sell so many of them. And the real constraints are, we have to make sure the average fuel economy, or miles per gallon, of the whole fleet of cars is at least a minimal value to meet regulation standards. Okay, so we want to figure out how many of each car we should make, such that we make less than the market potential, the demand, and such that we make enough cars that get higher fuel economies to offset the cars or the vehicles that get lower fuel economies. The real trick on this one is to make this a linear model. You have to be careful about how you set up the constraint for computing the average fuel economy for the fleet. Okay. And then there were a few changes that I suggested being made. So if you raise the fuel economy requirement from 27 to 28, how would the optimal solution change, and so forth. All right, so the next question involved another manufacturing kind of situation where we make two kinds of, what were these, alarms, an electrical or electronic and a battery-operated alarm detector. There were demands for how many of those we could sell. Obviously, it costs us time in certain departments or machines or people to pay to make these things, and we have a capacity of how many hours we have available. So to make one electronic unit takes 15% of an hour, and we have 2,000 hours available, and so forth. And then there is a variable cost per unit, that is how much we have to pay for the material we get, and then paying for those hours in the different departments, paying people, and then a profit per unit that we can sell these for. In addition to that, we had, so essentially the decision variables were how many electronic units to build, how many battery units to build, subject to the number of hours used to do those building is less than the capacities of the departments, and obviously we're trying to maximize the profit, the total profit, which was the profit of each unit sold minus the cost of each unit summed up. Okay. However, we also have two additional decision variables. That is, we can subcontract somebody else to do the building for us, in which case we don't need to expend our hours in our departments to build and assemble and ship. A subcontractor will do all of that for us. However, he will do it for a higher cost than what it costs us to build it, right? So it's cheaper to build ourselves, but we have limits on how many we could probably build. Or we can pay somebody else, and they can build another 20,000 units if we want them to, of any combination of electronic and battery operated, but for a higher cost, but still make the same profit. We could still sell the electronic units for $29.50, but we could pay a contractor $21.50 for each one they made for us. So again, there's four decision variables: how many electronic units to make, how many battery units to make, how many electronic units to pay the subcontractor to make for us, how many battery units to pay the subcontractor to make for us. And the constraints on what we make involve three different number of hours available. The constraints on what we subcontract, that is, we let the contractor make for us, is just a set number. We can't have him or them make more than 20,000 total units in whatever mix of the two kinds we want. And again, we're trying to maximize profit. Okay, so that was four decision variables. It looks like something probably like four constraints, and then obviously the objective. Exercise number 3. This was a binary optimization problem. So we want to pick and choose which of 8 projects to undertake. So we either choose to do it or not. So it's a binary decision, 8 decisions, one for each project. Each project comes with an expense for which we are constrained by a budget. So there's so much money we can put into the research and development of the suite of projects we choose to do. They also come with a number of scientists that it will require to undertake that project, to work on that project for us. And we have a set number of scientists available. So we can't choose more projects to do than the sum of the expenses would be over our budget, or the sum of the scientists required would be more scientists than we have available to do the work. And then each project comes with a potential profit that it would make, and we want to maximize that profit. So we want to choose as many projects as we can to maximize profit, subject to not violating a budget constraint and a scientist requirement constraint. So parts A through D just go through different portions of that problem, changing the constraints in one way or another, and adding additional constraints, like saying 2 projects are mutually exclusive. You can't do both. You could do neither one or just one of them, but not both, and so forth. So, any questions about any of those? Yes?
Could you bring your Solver sheet back up? I have a question about the
Okay.
demand string.
Okay.
So you're giving some product as a C10 to B10.
So the decision variables for how many things to make multiplied, in this case, it's just multiplied one of the products by one. I could just have easily have made this cell F21 just equal to C10. That's effectively what it's done. It's computed just E10, or I'm sorry, C10. And then cell F22 is D10, and F23 is E10. So it's just how many of each product one by one we've chosen to build. And we're constraining each of those to be less than their demand, each one multiplied by whether or not we make it or not. Okay. No more questions then? All right. Sounds good. Well, let's take a short break, and then when we come back, we'll jump into, actually go backwards in the textbook and start talking about Chapter 8 and nonlinear optimization.